Hello everyone, welcome to another lecture on PIC24 architecture. Today we will talk about program memory organization and also we'll talk about data transfer instructions and various addressing modes. We might already talked about some of this information in this slide, but it's important to emphasize, so I'll just go over them again. So microcontroller versus microprocessor. Microcontroller intended as a single chip solution. We'll talk about what that means, and microprocessor requires external support chips like a memory and interface. So like microcontroller has all of that in it. So it's like a one in all kind of thing. It has all kinds of peripherals, memory like I/O interface and timers and interrupt and serial communication peripherals. So it has everything in a single chip. But usually for microcontrollers, that those things, especially the memory and interface, is external. Microcontroller has microcontroller has on-chip non-volatile memory for program storage, and microprocessor does not. So you have to have additional RAM and beside your microprocessor, but in microcontroller you have that on chip. Again, another difference is microcontroller has more interface functions on chip, like serial interfaces and analog to digital conversion and timers and things like that, more than a microprocessor. Microcontroller does not have virtual memory. So what that means, it cannot run operating system, while microprocessor has virtual memory. Another difference is microprocessors obviously have a higher performance in terms of clock speed and data width and instruction set and cache. So in all these aspects, microprocessor has higher performance than microcontroller. But maybe again, we might talked about this before, that difference between microprocessor and microcontrollers are increasingly blurred. There's nowadays we have 32-bit microcontrollers and maybe even more. I'm not aware of. Maybe they have 64-bit microcontrollers. So we have 32-bit microcontrollers, and they are very, very fast. So so it's kind of, there are still differences, but that differences is getting smaller and smaller. Here we see a PIC24 core architecture. This is a very simplified version. So you can see the original one in the PIC24 data sheet, depending on what microcontroller you are exactly using. So you can look at that. We'll talk about that later. So let's look at each block here. So on the left, we have a program counter. Like here we have a program counter. Basically, program counter is a register in a computer or a microprocessor or a microcontroller that contains the address locations of each instruction being executed at a current time. As each instruction gets fetched, the program counter increases its stored value by 1. So it's 23-bit length. So what that means is it can hold up to 4 million instructions. And then we have program memory here. We have a program memory here. So again, this holds the program written on the microcontroller. So it's a non-volatile. That means if power is off, your program is still gonna be there. And here we have instruction register. It contains the machine code of the instruction currently being executed. So we are going to talk about machine code in a little bit. And then we have ALU. I guess all of you know by now what ALU means. It stands for Arithmetic Logic Unit. It's 16-bit wide and can accept as operands working registers or data memory. And here we have a data memory. This is a volatile memory, meaning if power is off, you use all the data. So in PIC24, so one important aspect of PIC24 is program memory and data memory is separate, and the program memory is non-volatile and data memory is volatile. As we mentioned in the previous slide, just review it again. Memory on PIC24 microcontroller family splits into two types. Again, one program memory and the other one is the data memory. So PIC24 instructions are stored in the program memory, which is non-volatile. Again, what that means is contents are retained when power is lost. And a PIC24 instruction is 24-bit wide. So in other words, it's 3 bytes, right? So each byte is 8-bit. So 3 times 8, 24 bits wide. And for our microcontroller, PIC24 FJ64GA002, program memory supports 22,016 instructions. The PIC24 architecture can support up to 4 million instructions. So PIC24 data is stored in data memory, also known as a file register. In PIC microcontrollers, data memory is called file registers. And the maximum size of it is 8,192 times 8. Again, data memory is volatile. Again, meaning if power is the information is going to be lost when power is off. If power is gone, then you lost all the information there. This is a diagram from a microcontroller data sheet. So as you can see here in PIC24, instruction width is 24-bit. Okay, so it's from here to here. So from here to here is 24-bit. So this is the program counter, right? So it counts the instructions, and obviously it's going to start from 0. And because it's 24 bit wide, the instructions 24-bit wide, so we cannot hold it in a single address location, right? So because address locations are 16-bit, right? So that's why we need like 2. If it is 24, we need 2 address locations. So what that means is what that means is basically one instruction is gonna hold 2 address locations. So this is gonna be like a least significant word is gonna like if let's say we are starting from like a program counter starts from 000, all zeros, then the least significant word is gonna be held in this address in the program counter as this, and the most significant word is gonna be held in this address. Okay, so again, like because it's a 24-bit, the instruction is 24-bit, we are not using the most significant byte here. So we call it phantom byte, basically read as 0, and they are unimplemented. Okay, they are unimplemented. So so then basically each instruction in the program counter, it's like a first instruction is gonna be stored in 000000 and 000001, and the second instruction is gonna start with the address 02, and the third instruction is gonna be 04. It's, as you can see, it's gonna be always even values. Well, PC is 23 byte wide, so what that means is you can have since it's 23 byte wide, that means you can have 2 to the 23, and because for each instruction we need at least 2 address, so if we divide that by 2, so it's going to be 2 to the 22, and this is going to be 4 million address. So PC, what that means is PC can address 4 million instructions. Here, location for our microcontroller, location from 000000 to 0001FF reserved, and user program, this is kind of for some internal stuff, so we cannot touch that locations. User program starts at location of location 000200. Here we have data memory organization figure for our microcontroller. These two figures from data sheet for our microcontroller. On the top we have SFR space, which stands for special function registers, and after that we have a near data space, so which we hold the variables and things like that, and then data RAM, and then program space visibility area. So here basically you can store the values. Let's look at this figure on the right. So like as you can see, the addresses goes from here 0000 in hexadecimal, and then 0001. So if you think as like a 16-bit like a word, word stand, like when we say word, it's basically we mean 16-bit. So you can either like basically it has a least significant byte, and it has a most significant byte, right? So it's 88 to make 16. So you can store a least significant bit, let's say in 0000, and the most significant bit in most significant byte in 0001. So our microcontroller is 16-bit microcontroller. To have a backward compatibility with the previous generations of the microcontrollers in PIC microcontrollers, you know, like before PIC 16. So sorry, PIC 24, we had PIC 16 and PIC 12 and so forth. So they were 8-bit microcontrollers. You know, like basically to make our microcontroller backward compatible with the previous generations of PIC microcontrollers, so we can store data in bytes, right? So like basically if it is a 8-bit value, then we can store it in just in one address, like in this location. Okay, so if it is a 16-bit, then we use both this address and this address location, right? So again, if it is an 8-bit value, then it's gonna we can store it in this let's say in 000 address location. If it is a 16-bit, then we utilize both these address, right? So because we store the least significant bit, so byte in here and the most significant byte here. And well, it can be even larger value. So if it is a long word, meaning like if it is a 32-bit value, then we need like a 4 address locations for that, right? So like we can store like the half of the like first 16-bit in here, which again utilizes 2 address locations, and then the most significant 16-bit in here, right? So that's how data alignment works in in our microcontroller. Okay, let's talk about special function registers, SFRs. Special function registers are addressed like a normal data locations, but have specific functionality tied to hardware subsystem in the processor. We typically refer the SFRs by name, let's say W0, like a working registers, T3 con, basically timer 3 control register, or status register, which holds, overflow and, things like that. We don't name them by their address. We have a special name for them. There are many SFRs in PIC24 and in any microcontroller, really. They are used as control registers and data registers for processor subsystems like the serial interface or the analog to digital converter and things like that. So we have special registers for those too. So as we go, we will cover that special function registers later. SFRs live in the address range from hexadecimal 000 to 07FE in data memory. So like in the previous figure, we showed that it's on the very top. So you can see all the SFRs in the data sheet. So it's like hundreds of pages talks about SFRs. Other locations in data memory that are not SFRs can be used for storage of the temporary data. They are not used by the processor subsystems. These are sometimes referred to as GPRs, general purpose registers. MPLAB refers to these locations as file registers. In microcontroller programming, we deal with data that is 8-bit or 16 bits, or in other words 2 bytes, and 32-bit, in other words 4 bytes in size. So these are the data that we deal with. Initially, we will use 8-bit and 16-bit, and we'll talk about also how to use 16-bit like a 32-bit data. Well, obviously you know this quite a bit. If you have 8-bit data, that means like basically it's gonna like the value, the unsigned range is gonna be 0 to 2 to the 8 minus 1, right? So it's gonna be 0 to 255. So if it is assigned, it's gonna be half, right? So it's gonna be half. Another word in hexadecimal, the range is going to be from 0 to FF. In 16-bit, it's going to be from 0 to 2 to the 16 minus 1. Another word is like it's from 0 to 65,536 in hexadecimal, or 0 to FF in hexadecimal. In 32-bit, obviously the range really grows significantly. So it's from 0 to the 32 minus 1, and in decimal it's 0 to like a 4 billion, a little bit about 4 billion, or in hexadecimal it's like a bunch of F's, right? So FF, 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 FF. Like just you know this stuff, but just to remind the lower bit of a 16-bit value or a 32-bit value known as the least significant byte, right? So the lower 8-bit, and the upper 8-bit of 16-bit value or 32-bit value known as most significant. Sorry, I said bit. It has to be should be byte. So the lower 8-bit for 16-bit value or 32-bit value known as least significant byte, and upper 8-bit of 16-bit value or 32-bit value known as most significant byte. How we store a multi-byte value in a memory. If it is a single byte, or in other words, a 8-bit value, then each data will can be stored in one address location, one memory location. So it's not going to be any issue at all. So, but if it is a 16-bit or 32-bit value, then one address like memory location is not going to be enough, because one memory location can hold only 8-bit value. So in that case, we have to use multiple memory locations. Like for example, assume we have 16-bit. Assume we have 16-bit value here. It's a 0x8b1a. Well, it's stored at location 0x100 1000, right? So here, well, obviously it cannot. The whole thing cannot be stored at that location. So what we do? Let's read here. 16-bit and 32-bit values are stored in memory from least significant byte to most significant byte in increasing memory location. So we call this little endian order. So remember from your previous courses. So what that means is, if you want to store this value starting from this memory location, so first we start with the least significant bit. So we stored least significant bit, which is 1a, right? So this is in hexadecimal. So each digit represents 4-bit, right? So and so the 1a is 8-bit. So we store 1a in this address location, and then we store 8b in next memory location, which is 8b. Okay, so that's how we store 16-bit value. Well, let's say we want to store 32-bit value at location in this location, which is right after the 16-bit value. So again, we start with least significant byte, and then we go toward the most significant byte. So least significant byte here, AC, right? So we store it here. Then we go to the next byte, which is 25, and then we go to next which is 90, and we go at the end, we have the most significant byte, so F1. So storing 32-bit value takes 4 memory locations. Okay, so this is memory shown in 8-bit wide, and here memory shown as 16-bit wide. So these two things are exact same, but you know, this shown in 16-bit wide, meaning you know, like address locations like this includes both 1000 and 1001, and then next location is 1002, and which includes 1002 and 1003. So either way, you know, just to sometimes to make life simple, we represent like that, but these two things are same thing. Least significant byte of 16-bit or 32-bit value must begin at an even address. Okay, so that's to have this is always true. So if you want to make it like a word aligned, so least significant the least significant byte of 16-bit or 32-bit value should start with even address. Just keep that in mind. Okay, so we cannot store. What that means is we cannot store 16-bit value here. Okay, so it should start even from here or from here. So it can end here, but it cannot start with the odd number. The address location cannot start, memory location cannot start with the odd number. It has to start with the even number. Again, either here or here or here. That's all. Okay, let's talk about PIC24 instruction set. So first instruction we're gonna talk about is data transfer instruction. Basically what it does, copies data from source to location, from source location to destination. So this is how we represent it, and basically what that means is copy the content of the source and put it in destination. So we have two operands, one is source and one is destination. Again, in this case we have two operands. The method by which an operand address is specified is called addressing modes, and we have various addressing modes in PIC24, and we will talk about some of them now, and we'll talk about some of them later. Okay, let's look at first data transfer instruction. It's a move .b if you are moving byte, and VSO comma VDO instruction. So this is the format of the instruction, the assembly instruction. Like basically what it means is, by the way, move is kind of unfortunate name for this instruction. We are not moving, we are copying. So when we say move VSO comma VDO, the meaning is copy the content of VSO register to VDO register. So this is the general form for the instruction. Okay, so, and I'll give you some examples. Again, we can, again, the meaning of this is meaning of, sorry, let me have my pointer here. So meaning of this is, again, copy the content of the source register to the destination register. Again, what is VSO? VSO is one of the 16 working registers, start of W0 through W15. S indicates VSO is an operand source register for the operation. So basically it's a source operand. That's what SO means. And video is one of the 16 working registers, again from W0 to W15. And D indicates video is an operand destination register for operation. So basically this was the general form. This is how we write in like in assembly, right? So move W3 to W5. Again, move content of W3 to W5. Default is a word operation. So if you don't do, if you just put in this format, basically it's gonna think it's a word operation. So it's a 16-bit operation, and it's gonna do that. If you just wanna do like an 8-bit like operation, like a byte operation, then we have to put .b. So here we can put .w, move .w, but not necessarily, it's not needed because it's gonna do like a word operation anyway. It's as a default. So if you want to do byte operation, then we have to put .b here. So it's the same thing. So what's gonna do is if you do this, move .b W3 comma W5, it's gonna copy the least significant byte of W3 and it's gonna put it in list significant byte of W5. So that's what's gonna be like. If you have like a 16-bit value in W3, it's not gonna copy all of it. It's just gonna copy the least significant byte and put it in W5. It's just gonna put it in the least significant byte in W5. So sorry, if you just do move.b, it's gonna copy the least significant byte of W3 and it's gonna put it in least significant byte in W5. Again, just to reiterate, it means content of working register W3 copied to working register W5. I explained the word and byte operation. So we are going to do examples. Hopefully this is going to help you understand better. The addressing mode used for both the source and destination operand is called register direct. Again, the addressing mode used for both source and destination operands is called register direct. The move instruction supports other addressing modes, which we will discuss later. Okay, so let's do an example here. First one is let's execute this move instruction. So move W2 comma W1. Again, what it means? It means copy the content of W2 and put it in W1. So here, this is basically the memory before we execute this instruction, and this is the memory after the executing this instruction. So, well, let's look at W1 and W2. So these are the current values. So it says copy the content of W2 and put it in W1, right? So so basically we are gonna apologize. So basically we are copying the content of W2 and putting in to W1. So what changed? So basically only thing changed is W1, right? So basically well, we had this value in W1 before, so we just copied the W2 and put the value, the content of W2 and put it in here. So basically the previous content gone, so new content is copied from W2. So everything else remains same. So like W0, we didn't do anything with W0, W3, we didn't do anything with that, and W2 we just copied. We didn't modify the content of W2, we just copied it and put it in W1. So this is before and this is the after. Well, this was a word operation, so meaning it's 16-bit, right? So like, you know, like this like content of W2 was 16-bit, so we copied all of it and put it in W1. So very straightforward. How about like a byte operation? So like in the second example B, we have move.b, same thing, but this time it says byte operation. Again, if what that means is, like remember from previous slide, copy the least significant bit, copy the least significant byte of W2 and put it in least significant byte of W1. So we are copying least significant byte of W2, which is DE, right, in hexadecimal, and we are putting in to least significant byte of W1. So again, before in W1 we had 8B1A, because we copied these two, like this 8-bit here, and you know, like 1 byte, and we copied here. Only thing changed is here. So instead of 1A, now we have DE. 8B didn't change because again we did byte operation. So we are not copying whole content of the W2. We are not copying the whole word here, right? So it's a byte operation. So we are copying the least significant byte and we are putting in here. So that's why nothing else changed. W0 didn't change, W2 didn't change, W3 didn't change. Only thing changed is the least significant byte of W1. 8B remains same because we did the byte operation, and that's about least significant byte of W1. So before and after. Okay, so let's convert assembly instruction, which is move, move instruction here, to the machine code. Okay, so if you look at the programmer's reference manual, you will find this move instruction in the reference manual, and you will get all this information from that, like the information about that instruction in the programmer reference manual. So we just copied that information here. So again, as we can see, it's a 24-bit wide, right? So the machine code is 24-bit wide, and so this is the format. So you see here a bunch of things, for how we're gonna like basically the format of the machine code. This instruction, like assembly instruction, is gonna be converted to machine code, and this is the format. So here we have www. This is the base register. Again, this is for indirect addressing mode. So we are currently not covering in the indirect addressing mode. So we are currently doing direct addressing mode. So register direct addressing mode. So in that case, if you are using direct addressing mode, then it's gonna be 0. So www is gonna be 0 in our case. let me have my pointer again. Again, what I mean is like this is our format, like this is for the machine code, and we are gonna try to figure out what should be these values, like for example www and capital B, HHH, DDD, and so forth. So we are gonna figure out what each of these values are, and that way we are gonna be able to convert this assembly instruction into machine code. Again, here it says www, it's a base register for indirect offset addressing mode. If you don't understand, don't worry about it. Just ignore it. Okay, you don't need to know for now. Currently, we are using direct addressing mode, right? So like this is basically direct addressing mode, and so that's why if it is a direct, if it is not indirect addressing, then it's gonna be 0. Okay, so in this case, since we are doing direct addressing, we are in addressing, so the value www is gonna be 0. So then what else? Right, this is direct addressing, so it's a move w3 w5. So like sorry, before I just move ahead, like this 0 1 1 1 is gonna be constant, so we are not gonna change that. This is about basically indicates what instruction it is. Okay, so this like the first 5 digit, in this case we are not touching those, so like it just indicates what kind of instruction, what instruction it is. So that's why, so 0 1 1 1 1 is gonna remain there, and then www is gonna be basically all zeros, right? So then we're gonna have, because again it says here, if it is not indirect addressing, then it's gonna be 0. Okay, so then we have like 4 zeros, so like 1 2 3 and 4. And then we have B, capital B. It says B is 0 for word and 1 for byte. Well, here we are doing word operation, right? If it is a byte operation, it should have like a .b. So if it is not byte operation, then as a default, it's a word operation. So for word, it has to be 0. So then B is 0 here. Okay, and then what else? HHH. So let's see what HHH means. So video addressing mode. So for register direct, it's 000, right? Well, it says there like for register direct, it's 000. So that's why we have 0000. Okay. How about VDD? Sorry, DDDD. So like we took care of HHHH. How about DDDD? That is video register number. Well, what's our register? Video. So this is our video and this is our VSO, right? Our video is W5. Well, how can you represent W5 in 4-bit, right? So we have again, let me show you very quick here. So we want to represent so our video, in this case W5, right? So we have registers, working register from W0 to W15, so we can represent them in like a 4-bit, right? Like so 4-bit value. So like W0 is gonna be 0 0 0 0, and W1 is gonna be equal to 0 0 0 1, and so forth. So W5 is gonna be equal to 0 1 0 1, right? So it's basically 5. Okay, so that's why we have DDD is gonna be 0 1 0 1. Okay, so VSO, which is the source, which is W3, well, W3 is gonna be, obviously, you know, if you go this way, so W3 is gonna be 0011, right? So 0011, that's equal to 3. So yeah, so we took care of DDD and GGG, and then the last one is SSSS. No, we took care of that one too. Oh yeah, here this is GGG. The addressing mode. Well, for registered direct, it's in like a 000. This value is going to be 000. So how we know that? There is a table in the data sheet that shows all that stuff. Okay, so if you go back to the data sheet and or programmer's reference manual, I'll have a, you know, more information about that. Again, all this information, you know, you get it from, you know, like either data sheet or the reference manual. So yeah, so we got SSSS, which is you know, like a W3, which is equal to 0011. We got DDD, it's 0101. GGG is, if it is a registered direct, if it is a direct addressing, it's going to be 000. And same thing for HHH, if it is a direct addressing, it's 000. So yeah, so we were able to convert this machine, so this assembly instruction, into machine code. Okay, so this is like a really true one and zeros, right? So like, you know, in VARTs, you know, we always talk about, you know, computer does everything in ones and zeros. That's how it does it, right? So like a machine code is the lowest level, right? So and that's the lowest level, and it's truly consists of ones and zeros. Again, all these are 0 because we didn't use indirect addressing here. So again, you can find these values in a table, which I will show you in next. Okay, so let's look at another format for move instruction. This time it's not from working register to working register. It's working register to data memory. So this format, what it means is copy the content of the WNS register to data memory location F. Okay, and again, it's this. If you see the symbol here, that means copy the content of this register and put it in this memory location, data memory location. F is a memory location in a data memory, and WNS is one of the 16 working registers. Again, V0 to V15, as we mentioned before. S indicates that WNS is an operand source register for the operation. So it's the source. So if we have, like, let's say instruction like this in our code, assembly code, what that means is content of register W3 copied to data location, you know, in 1000 in like the address is 1000 in hexadecimal. This instruction only supports word operations. Okay, so how can you know that? Like, you, again, in the programmer's reference manual, So basically 90% of programmer's reference manual talks about the instructions. You have a list of the instructions. So like basically they grouped in under different group, like there are different types of instructions. So you can see them in different groups, and then there's a single page or a couple page explanation of each instruction. So you can get all that information in detail from programmer's reference manual, which I will show you later. Again, here the source operand uses register direct addressing, while the destination operand uses file register addressing. Again, file F is basically file register, or F stands for like basically means memory location in data memory. So it means a data memory basically. Yeah, and again, it's here actually says the same thing. File registers is how microchip refers to data memory. Okay, so we have working registers, which is like 16 of them from W0 to W15, and it's not much, right? So it's very lean and very small. So, and then we have data memory, which is much larger, and then you can store more stuff there. So file register is again how microchip refers to data memory. So here's an example. We want to execute this instruction. We want to, again, it's a move W3, comma 0x 1002. So W3 value is given here. So the content of W3 is given. And so, well, so this is the data memory location, and its content, like the before, and this is the after. So basically what's going to happen is, again, we are going to copy the content of W3, and we will put it in address address location 1002. So we just go in the data memory, we go here, and we put content of W3 there. That's it. Nothing really, nothing really major here. So like what's changed from like a before and after with this instruction. So this was the current, like the before the instruction executed, and this is after. So nothing else changed except the content of this address, right? So again, W3 is unaffected because we are just copying content of W3. We are not changing the content of W3. We are just copying it. Okay, so let's look at move instruction, like how to convert the same assembly instruction in the previous slide into machine code. So again, you can find all this information here. So all this information from here, from the programmer's reference manual. That's our go-to document for like any kind of information about instructions and for some other things. Here, so this is the format. As you can see, we have like 1001, like 1000 here, and then 1 here. So we don't change anything here. This is about like the value there, the constant value. We are not supposed to change, and basically it's about what instruction we are using. And then we have FFF, FFF, FF, and so forth, like a bunch of Fs. And F is basically the address, indicates the address of the file register or data memory. Okay. And SSSS S is basically the WNS register number, again, like working registers. We have 16 of them from W0 to W15, so that indicates that well, here there's a note here, so the f dot 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 f is basically 15-bit of the 16-bit address. So what we need to do here, so let's say this is given, this address is given to us, it's 1002. Of course, this is in hexadecimal, so what we have to do is we have to convert that to decimal, right? So that's what happens here. Okay, so we convert using either like a calculator in your Windows. In the programmer mode, you can easily do that, or you can do it manually or with a calculator or online. So you convert this hexadecimal address here, file register address, into binary, and that's the whole. This is gonna be what you get, and you ignore the least significant bit. That's what it says, because remember like when you in the addressing, like when you like it should start with the even numbers, right? So it cannot be 1. Okay, so it has to be the least significant bit, has to be always 0. Remember the word alignment in our previous slides, it has to start with 0. So that's why you skip that one. So if like you convert this hexadecimal number to binary, this is what you get, the whole thing. You ignore this 0 here, and then you take the rest and put it here. It's like you have 15 FFFF, so then you put it there. And well, then you have SSSS. Again, it's a working register, and it's a W3, and for 3 that's 0011, and that's it. So that's the machine code in binary, right? So 24-bit machine code in binary, and if you want to convert it to hexadecimal, you can just group them by 4 by 4, and then you can convert it to hexadecimal, and that's what you get. Okay, so this is similar thing, but it's just kind of opposite. Now, instead of copying content of working register to file register, now we're gonna cover like copy content of like a file register to working register. Again, it says here, copy the content of data memory location or file register F to registered like a working register. And this is the general format. This is general format, and basically this is symbolic version of what we mean by basically this means copy the content of F file register or data memory location to working register. F is again, like we said multiple times by now, F is the memory location in the data memory, and WND is one of the working registers, W0 to W15. D indicates the destination. So if we have something like this, okay, and what that means is basically copy the content of this memory location into this working register, W3. Again, parentheses read as content off. Okay, so that's when we read this, it means copy the content of this file register location into W3. And this instruction again only supports a word operation, so you cannot do byte operation. Here's an example implementing it. This is the line of code in assembly we want to execute, and W3, so it's basically we are gonna copy the content of this data memory location into W3. So currently in W3 we have this value, and in this memory location we have this value. Well, what's going to happen? Well, we are going to copy content of this memory, like whatever in this memory location, the copy the content and put it in W3. That's it. So this is before and this is after. Nothing changed in the memory location, the content of memory location, and nothing changed. So only thing changed is the basically content of W3, which what we expect, right? Well, at this point, you can say, well, what's going on here? I mean, I'm not I was not expecting this kind of stuff in this course. I was expecting programming microcontroller. This is kind of too much, and or why we have to learn this. Well, you are kind of right. Our purpose is not, we are not gonna code in machine code, right? So we are not gonna do that. But we are going to do few things in assembly. Again, there's a benefit doing things in assembly, and there's a benefit understanding things in assembly. And there's benefits understanding the machine code when it, like in some cases you might need that, right? So like, it's better to know and understand what's going on under the hood, really, you guys are gonna be engineers, so it's like what separates you from being technician, right? So you really know what's really going on under the hood. So in that sense, it's important. So we are gonna talk. We are talking about this stuff, but we are not gonna talk about throughout the semester. So I just want you to give some basics and understand what's really going on. But later on, we will mostly do things in C, and we will use assembly as we need it. Like I said, studying machine code formats of the instructions is not our priority. Understanding instruction functionality will be emphasized, right? All the instruction formats can be found in Programmer's Reference Manual. Again, that's our go-to document. So all the information is there. So whatever I'm talking about in the class, or anybody in that matter talks about, this specific microcontroller, they get the information from either data sheet or Programmer's Reference Manual. That's basically that's the document prepared by the engineers. The engineers designed that microcontroller, so everything is there. It's our that's how we learn things for this particular microcontroller. Another thing is PIC24 is a family. PIC24 family is a subset of DS PIC30F instruction set. In that instruction set, like there's a bunch of other DSP, digital signal processing instructions and things like that. Our microcontroller does not support that. So the PIC24 family does not implement DSP instructions. Okay, so just if you see bunch of more instructions in some documents that like related to digital signal processing, PIC24 is not implementing those. Okay, here we have another instruction. Again, you can say, like, we learned about move instruction, but if you look at the instruction list, like there are like I don't remember exactly the number, but you have like even like maybe more than 10 move instructions. Don't quote me on that, but there are many move instructions. So this is move.b wreg f instruction. What does that mean? Copy the content of a WREG, and WREG means W0, okay? Again, default working register. Copy the content of WREG to data memory location F. Again, that's the general format we see here. I mean, let me show with my pointer. So that's the general format. This instruction provides upward compatibility with earlier PIC microcontroller because you can do byte operations, right? So, you know, like so that, you know, this instruction supports basically the compatible with the previous generation microcontroller. WREG is a register, W0 as I mentioned, and F is a location within the first 8192 bytes of data memory. So if you remember that figure, like figure I showed, basically that's basically near data memory. So like just below, like you have on top, you have SFRs, and under that you have working registers, and then under that you have near data memory. And let's say we have this, we want to do this, so we want to move like this instruction, we want to execute this instruction. Again, what does that mean? Copy the content of W0 into this F register. Yeah, like a file register. So like what's like you can, yeah, so like this, the difference between this one and previous instructions, again, this can do byte instruction, and also this is using not just any W register like working register. This specifically uses W0 only. Okay. Again, the meaning of it here, as I repeated many times, so this can do byte and word operations. Like it can do either, right? So if you use .b here, it can do byte. If you don't use .b, then it can do word operation. Okay, so this does the word operation, and this does the byte operation. Again, remember, word copy must be to even. Remember again, like the previous instruction cannot be used for byte, so this instruction, but this instruction can be used for byte operation. Okay, so let's look at this example here. So we want to execute move.b wreg, comma 0x001, yep. And what that means again, copy the least significant byte of wreg or W0 and put it in to address location 1001. Okay, so that's what we're gonna do. Well, this is the before executing that you know, assembly instruction, and this is after. So before executing the instruction, we know W0 or WREG, and so basically what's happening here is we need to copy that into the address location 1001. Okay, so here locations are given in so address locations are given in like in the word format, so not 8-bit by like a 8-bit. So like basically this part is 1000. Okay, so this address location, address that let me put it here very quick. this value is in address location here, and this value is in address location here. Okay, so and then like basically you have remember the like you remember the if you do it like 8-bit, so like this is address location and this is the address location next, and then if you go down, so this is gonna be this is gonna be 1000, and this is gonna be 1002, and this is gonna be 1003. So if you do like 8-bit, so that's how it's gonna look like. So like again, this is address, this value is the first least significant byte in here is located inside this location of the address, and this part is in here. Okay, so that's why if you want to copy the content of the W0, the least significant byte of W0 into here, so this is that location. Okay, so that's why we put 4F there. So what changes? Like, what's the difference between before and after? Everything is the exact same, except now instead of 8B here, we have 4F. That's it. Okay, so similar to what we did before, let's look at how can we convert this instruction, assembly instruction, into machine code. So again, this information is from Programmer's Reference Manual. If you look at this specific instruction there, so you will find a detailed explanation there. So here we have again the 24 digit binary number here, and again these are the constant value. We don't change any of these, and until here. B, again, if we do byte operation, it's going to be 1. If it is a word operation, it's going to be 0. And then we have one constant 1 here, and then we have 13-digit F. Okay, and this is for, again, address location, like a file register location. So, well, using that, you can figure out what should be the machine code. Let's do it for this one. So I'm just gonna do it for this one here. So here we're gonna have again like 1 0 0. Oh, sorry, my bad here. It's so 1 0. Again, I'm just looking at here. 1 0 1 1 0 1 1 1 1. So this is not a byte operation, so it's gonna be if it is a word operation, it's 0, so it's gonna be 0. And then I have 1 1 here, and then I have 13-digit binary value for this address location. So what's the equivalent of 1000 in binary? So let me figure that out. So we have to be careful here. So we want to represent 1000 in 13-digit, right? So this is a hexadecimal value. So 0 is basically in binary 0 0 0. So this 0 can be 0 0 0, and this 0 is 0 0 0 0. I mean, like 4 zeros, sorry. And 1 is basically 0 0 0 1, obviously. So, well, we have like 4-digit, 4-digit, and 4-digit here. So since we're gonna have 13 digits, so we can we ignore like basically this zeros doesn't change the value of the number, right? So we can just say 1 0 0 0 0 0 0 0 0 and 0 0 0 0. So if you convert this to binary, so I mean the hexadecimal back to hexadecimal because that's what's given. Let's see if we got it right. So this is 0. So this is 0 in hexadecimal. We group by 4, 0. And what is this? This is basically 1, 2, and 8. So 11. So 11 is B. Sorry for my writing. So this grade, this is going to be B, and then next 4. So this is going to be 7, obviously, and this is going to be B again. So we got it right. Okay, so let's do this one, and let's do this one, see if we can get the same value again. W, the move.b, vreg, and 0x001001. Again, if we do this, like looking at this format, so it's 1 0 1 1 0 1 1 1 1, and it's a B is in this case it's going to be 1 because it's a .b operation. So now we are working on this. We worked on this one, now we are working on this one. So B is going to be obviously 1. It's a byte operation because we have .b here, and then F is going to be the binary equivalent of 1001, right? So what's going to be that? Again, if I do it same thing, you can, well, it's going to be 1 0 0 0 0 0 0 0 0 and 0 0 0 1. Okay, again, same thing, I ignore this, like in that case this is going to be 0 0 0 1 and 0 0 0 0 0 0 0 0 here, and this is going to be 0 0 0 1. I can ignore because I have only 13 bit look at F here, like 13 of 13 location, so I have to ignore the first 13, like first 3. And then if I do this again, 1 0 0, and this is F, and this is did I miss something here? This is B, obviously. No, let's just go back. I think I missed something. Let me double check what I did here. Oh yeah, well, no, just a second. So it's a 1 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay, and then 1 is for that one, and then 1 is for that one. Did I group wrong? Why I have a 1? I'm just gonna remove the whole thing and just let's do it from scratch. Okay, so let's do this again. Again, let's just look at this format. It's 1. I'm doing this one. Okay, so 1 0 0. Oops. 1 0 1 1 0 1 1 1, and then 1 more, and then B is going to be 1, as I said, and the 1, there is another 1 there, and then now we have 13 digit F value, and if you convert 1001 to 13-bit binary equivalent, it's going to be 1, and then 0 0 0 0 0, 0, 0, 0, and 0, 0, 0, 1. Okay, so that's the binary equivalent of 1001. So now we can group them again to, like, this is going to be 1, this is going to be 0, so this is going to be 0, and this 4 is going to be F, and this 4 is going to be 7, and this 4 is going to be B. Right? So we got the right answer. So you can do the same thing for the middle one. In that case, it's the exact same. Instead of 1001, it's 1000. So it's the same thing. Hopefully this helps. Again, if you have any question, please let me know. Okay, so this is just like similar kind of instruction. It's just the opposite. This time we are copying the content of file register into working register. This is the general form. Okay, so let's look at this explanation. Again, this instruction provides upward compatibility with earlier PIC microcontrollers, because it can do byte operations. vreg is again means W0, and F is location within the first 8192 byte of data memory. Again, the near data memory we talked about before. Can be used for either word and byte operation. Again, where do we get this information from? Instruction from programmer's reference manual. And if you go there, if you find the instruction, you can get all this information. And so this is how the format for. Let me have my pointer there. So this is the this is format for word operation, and this is the format for byte operation. Or we can, here we have another format like here I didn't mention. Well, what this does is copies the content of this value, like a content of this address, into itself, back to itself. Well, obviously it's we'll talk about how this can be useful later. Okay, so it might sound ridiculous to do such a thing, copy its content back again. It's just kind of useless, seems useless, but it's not, so we'll talk about that later. Word copy must be from even word aligned data memory location. Okay, as always, because of we have to satisfy the word alignment, so it has to be even location. Again, okay. Let's look at this one. How can we convert this into machine code? Again, this information we get from the programmer's reference manual. And let's say if this is the instruction that we want to do, like an assembly instruction, and this is the machine code equivalent in hexadecimal. Let's see in binary. Let's see if we're gonna get that. Well, again, looking at this one, so like this is the format, right? So this is the format we need to follow. And for this one, I'm just gonna put it here, and we have a constant stuff there. So 1 1 1 1 1 1 1. So this is not, like, this one is not byte operation. So if it is not if it is a word operation, then it's going to be 0. And the destination is 0 for vreg and 1 for f. Here, what's the destination? It's wreg, right? So wreg is the destination, so it's going to be 0. I mean, this is the source and this is the destination. And what else? And then we have 13-digit binary equivalent of the address location, like for F. Well, we know that already, so it's like from previous example already. So it's 1 1 0 0 0 0 0 0 0 and 0 0 0 0. Again, this is the binary equivalent of this like hexadecimal value, which is the address location in data memory. Well, then if you convert this to hexadecimal, back to hexadecimal, 0 0, another 0 here. So this is gonna be 9, and this is gonna be F, and this is gonna be what? This is gonna be B. Okay, so this is yeah, this looks like it's fine. So you can do similar stuff for this one. So the only difference is gonna be this B is gonna be because it's dot B. This B is gonna be 1. You know, so like let's just put it here. Again, it's gonna be 1 0 1 1 1 1 1 1 1. B is gonna be this capital B is gonna be for byte, it's gonna be 1, and D is gonna be still 0, and then you have F again. This part is the F, so it's a 1 0 0 0 0 0 0 0 0 0 0 0 0. So if you do that, so you get 0 from here, 0 0. So this is 13. I mean, this is let's see. Oh, sorry, my bad. This is like I was kind of thinking. Yeah, what I'm thinking here. I did it totally wrong there. So we have 1 1 1 1 here, and then in this case we have another one. This is byte operation, so it's 1. D is gonna be, now in this case, because like this is copying content of F to F, so destination is also 1, right? So it's a 1. Okay, so that's one I kind of didn't pay attention. So again, this means copy the content of F to F, right? So again, so source is F and destination is F2. So if F is destination, then it's going to be 1. And then we have 13-digit F. So it's going to be, you know, that's equivalent of 1 0 0 0 0 0 0 0 0 and 0 0 0 0. Again, I'm not including 3 leading zeros in binary equivalent of this one. So, well, then obviously now we got it right. So 0 0 F F and B. So that's it. Hopefully this was clear. Please let me know if you have a question. Okay, so this is an example of the same instruction. You know, like let's see what's going on in the memory, and this is what's going on before, right? So this is before, and this is after. So this is the instruction. It says move.b. So this is byte operation. Copy the content of least significant byte of the content of this address into WREG. Okay, so Well, here address is given in like in a Word format. So like this information, this content is in 1000, and this is in 1001 in 0x 1001. Okay, so so that's basically what we're gonna do is we're gonna take that value content of this address location and put it into W0. So before this execution, this is the content of W0, and after execution, so we're gonna take this content in this address location, which is 8B, and we're gonna copy it to least significant byte of W0, right? So W0 is 16-bit, and we just gonna or 2 bytes. So we're gonna put it in the least significant byte of W0. So what changed from before to after? So nothing else except least significant byte of W0, because this instruction asks us to, like, basically what it does is copies the content of this address location into least significant byte of W0. And this is before and this is after. Okay, so let's talk about literals. So far we copied the content of either a file register or working register into another working register or file register, right? So, but we can copy the literal into working register, and literal means a constant value, okay? And we have this pound sign indicates the numeric value as a literal, and not a memory address. Okay, so if you don't have this pound sign, what that means is basically it's like a computer, like a compiler will gonna take it as a memory address. So if you mean literal, so you have to put pound sign before that literal. So general form is like this. So basically you have 16-bit literal. Okay, so that's what that means. And copy this 16-bit literal into this destination working register. Okay, so as you can see here, we don't have parentheses because parentheses means content of. So we don't have that parentheses because the content itself is this literal now. So we are not going any address to find the content. So we have the content. It's just that literal we have. And we are copying that literally into that destination register. So if you want to copy, like if you want to copy like a byte literal, 8-bit literal, then we put .b here. And so here we have for byte literal, this is the instruction, and this is for word literal or 16-bit literal. The source operand in this example is immediate address mode. Okay, so again, if what this means, again, examples, move 1000. Again, this is not an address location. This is literally a constant value. Basically, it says copy 1000 into that working register W2. Just put this value in there. So there is no going to the address and finding the content. Just move this value into W2. And same thing here. This is 8-bit number, right? So in hexadecimal. And copy this hexadecimal AB into this working register. Of course, working register is 16-bit. So because it's .b, we are going to copy and put it into least significant byte of working register. Okay, so more on literals. Observe that following two instructions are very different things, right? So this one means copy hexadecimal value 1000 into W2. So after executing this instruction, W2 is going to be equal to this hexadecimal value, 1000. Content of W2 is going to be 1000. Basically, again, we just copied this literal because it has £sign before it. That means it's a literal, it's a constant value, just copy it into W2. The next one, this one, it seems like it's a very like same thing, but again, in this case, we don't have a $sign. So here, so we don't have $sign. What that means is like your compiler will take it as address location. So after executing this, what we're gonna get is W2 is gonna be equal to the content of this address location. So whatever in here. Okay, so you go to data memory or file register, same thing. You go there and so basically find the content of this address location, and basically W2 will be assigned to that value. Okay, here are a few more examples. Like for this one, execute move $0x1000 again to W2. This is called immediate addressing. So this is before executing this instruction. This is before, and this is after. So basically, what we're gonna do, we're gonna take this value again. This is literal, and it's a constant value, and we will just put it in W2. That's it. So the only thing we did here is we put this constant value again, because it's $sign here, it means a literal or constant value, into W2. That's it. So that's what this instruction does. Let's look at the next one. Here it says move 0x1000 comma W2. Well, this is like in the previous slide. This is the address location. So we cannot copy 0x1000 like 1000 into W2. We have, this is an address location in the memory, in the file register. So we have to go and look at what's in here in this address location and copy that into W2. Let me go there. So we go there. Well, in that address location, what's in there? 8B1A, and then we copy that into W2. Okay. And last one is, let's look at the last one. Execute move.b. Again, we have $sign. That means this is literal, and into W2. Well, this is again, we did similar example before. So this is not an address location or anything. This is like a literal value. So we will copy, it's a .b, so we will copy this value and put it into least significant byte of W2. So like before, like basically take this value and put it in here. So only thing modified here is W2, and only the least significant byte of W2 is modified. Nothing else changed. Okay, let's look at here and see how can we convert this assembly instruction into machine code. Again, this information can be accessed from programmer's reference manual, and here we have this instruction, and it's this is the machine code equivalent, and this instruction, assembly instruction, and this is machine, like a machine code equivalent. Let's do both of them and see if we can find the answer. So like for this one, it says copy the literal 1000 into W2, and this is the format for that. This is like 16-bit literal, so we're gonna use this one. So for this one, I'm just gonna put it here. Oh, maybe let's do this one here. Let's do this one here. We don't have much space. So we have for this one 0, 0, 1, 0, and then K is what? K is the literal. How many digits? 1, 2, 3, 4. So 12. So it's a 12 digit. 1, 2, 3, 4. So 16-bit literal. So if you convert this to the binary equivalent, so if you can just do it in the 16-bit, it's going to be 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and that's it. And then DDDD is where basically the register, working register value. So W2 is going to be 0, 0, 1, 0. Well, then what's going to be the hexadecimal equivalent of this one? So this is 2, 0, 0, 0, 1, and 2. Well, you see we got the same value. It's just this is in hexadecimal format and this is in binary. We got the same thing. So let's look at this one. So this is like an 8-bit literal, so we have to use this one, this format. And well, it says 1, 0, 1, 1, 0, 1, sorry, 0, 0, 1, 1, 1, 1, 0, 0. All that stuff is just automatic, so we just copy from here. And then it says, since it's 8-bit number, literal, so we just convert F2 into binary. So it's going to be 1, 1, 1, 1, and 0, 0, 1, 0. And then destination is W7. So W7 is in binary is 0, 1, 1, 1. Okay, so if you convert this to hexadecimal, just to see if we get the same answer here. So this is 7. This is 2. So this is 7. So this is 12, and in which in hexadecimals equals to C. And this is 3, and this is B in hexadecimal. So B3C727. So B3C. Sorry, this is F, by the way. Sorry. Yeah. So B3CF27. So we got the same answer. Hopefully this helps.